Okay.
No. Hi, everybody. It's a great pleasure to welcome Zofia Malish here at the University of Campinas to do her lecture. Zofia is a postdoctoral researcher in speech technology at the KTH in Sweden, and her work focuses on modeling speech prosody, especially rhythm, timing, and prominence, multimodal dialogue, especially prosodic modeling of feedback functions, head gestures, and phonation, especially glotalization and VOT. She was also involved in developing listening behavior in artificial agents and in building multimodal corpora. At KTH, she's responsible for the modeling of prominence in a text-to-speech synthesis project, Wikispeech. Please, the floor is with you, Zofia. Thank you so much.
Thanks so much, Plinio. And first of all, I would like to thank you and thank Plinio and thanks Prosig for inviting me. This is a great honor for me because I consider this special interest group in prosody at ISCA my kind of like home organization and really like a community that I identify with very much as a prosodist and a speech scientist and a speech technologist. And I have to say, yeah, it's always nice meeting you guys at Unicamp. I came to visit Brazil and Campinas, which is always a big event for somebody from Europe and your beautiful city and country. It was already almost 20 years ago. Imagine that. I was a very young student, so I came, I think, for the first time to visit your lab in 2008, and then there was this speech prosody conference in Campinas. I think the last speech prosody conference in South America. There hasn't been any since then, so I think it's time for big ISCA conferences to come back to South America. No pressure, but
it's already done. We will have Interspeech 2027 in São Paulo.
Oh, really? Oh,
yes.
Great. Well, that has already done my day, if not the year. This news. So yeah, I'm really happy to be seeing you again and students at your university, and also wanted to say hi to everybody watching. Okay, so without further ado, let me tell you a little bit about my research and the promise of speech technology for phonetics. How? Let me check here. Yes, are we now visible? Everything's fine. I'm just trying to catch my.
Yes, it's okay.
Just a second. One more time because I kind of wasn't able to catch my cursor. Move maybe this one back. Okay. All right. So today I wanted to talk about to you about the promise of the new neuronal data-driven based speech technology techniques and methods that have really developed recently and have done have undergone a lot of progress. And particularly, I'm going to talk about speech generation methods, speech synthesis, and try to relate how this progress can be used or what is its promise and how can we realize the promise for phonetics, particularly looking at speech synthesis as a kind of a method as a methodology in phonetic experimentation. So my claim for this lecture will be that the speech synthesis as a method that phoneticians need is both realistic and controllable, and I will explain what realistic and controllable mean in detail. And this is going to be more of a survey and also a sketch of a roadmap towards modern synthesis tools for phonetics, and kind of realizing this promise of the modern data-driven neuronal speech generation methods in our prosodic and phonetic field. Right. So the goals of this research is of this presentation is to discuss the needs of speech science regarding speech synthesis capabilities, and to discuss how far has speech technology actually come towards fulfilling those needs. So I will present some results of my work over the years and sketch research perspectives that advance both speech sciences and technology. So this is very important to me that, and I think this is the way we can come forward if we have a renewed and an intensified dialogue between speech scientists and speech engineers. And I think our association, both PROSIC and also ISCA, with the interspeech conferences, joining, bringing together those communities so that they talk to each other, and kind of the phonetician can express his or her needs towards engineering, and be able to perhaps act as a kind of a, let's say, client for speech technology, so that we can use the new modern tools based on neuronal networks and data-driven machine learning in our daily practice, right? So here in this picture, you see also my main collaborators when I will be talking about the results of the new methods and the improvements that we have done in this team regarding controllable and realistic speech synthesis. I will be mainly talking about the collaboration with these two colleagues of mine, Pablo Perez Zarazaga, my former postdoc at KTH in the middle, and on the right, Lauri Juvela from Aalto University. So this is us presenting last year in Dublin, one of our systems that are both controllable and realistic. I also worked with Gustav Henter from my native, from Sweden, from KTH on this. Okay, so starting with speech technology and what realistic actually means. So for speech engineers, the measurement and kind of the evaluation of realism of speech synthesis and speech synthesis systems is usually measured using very, very, very simple methods. So usually when you evaluate speech synthesis systems and you want to ask a question whether this particular speech synthesis system sounds realistic to you, you use this particular scale, a very simple scale, which is called the mean opinion score. You present to your listeners in your subjective evaluations. You ask the listeners to basically rate the signal, the synthetic signal, compared to another system or a natural speech reference that was recorded from a real speaker. And you present these samples to the listeners, and they are supposed to rate the different samples from different speech synthesis systems on this simple Likert scale. Sometimes it is usually from 0 to 5, where 5 is the best score, excellent, and 0 is very poor and not good at all, right? So this is something that has become something of a standard in speech engineering. People have been using this for years. This is not particularly finely grained and not particularly sophisticated. And you may already realize that in terms of how useful it might be for us phoneticians to judge whether the redundant speech features that we so care about are actually contained in the synthesis signal. This particular incredibly simplistic scale is not particularly useful. Other problems with MOS, the mean opinion score, sometimes pronounced MOS, is that the results of these ratings actually really depend on how you ask the question about the realism, the quality, or the naturalness of the signal that you are comparing and judging the quality of using this very simple scale. So this particular evaluation of speech synthesis realism is basically plagued by not only its simplicity, but also well, it's not very robust. This method of evaluation is not very robust. If the result of the evaluation and the result of the rating actually depends on how you ask the question. If you ask the question, so my colleagues from KTH have shown last year, they discussed this effect that if you ask the listeners that are rating the speech synthesis samples to rate quality, so you ask basically in the question, in the evaluation, how do you rate the quality of the signal versus how do you rate the naturalness of the signal? The average MOS will be then higher in the quality question rather than in the naturalness question. So so this particular method is not particularly robust and cannot really be used as a guide or a guideline or some kind of a robust evaluation measure if we treat it seriously from a rather more linguistic experimentation point of view. So this already suggests to you how the worlds of the speech engineers and how they treat their signal and how they evaluate their signal, how they understand naturalness actually, how this differs from how phoneticians might actually, what phoneticians might actually want from speech synthesis. This has, of course, a lot to do with the goals that we are pursuing. So usually when speech engineers or people that work in the industry ask what do they mean by the quality and the naturalness, it is a little bit, they probably do not mean that the actual direct voice onset time duration for that particular language that you are modeling is this or that long, and that kind of is corresponding to what a native speaker might do. So this is not even on, of course, it's not on such a finely grained level, but it is more a question about the acceptability by the users of, for example, mobile phones, whether the users of the mobile phones, when they hear a speech generated or Amazon Alexa or whatever, some voice assistants, whether they accept this quality of the signal as coming close to human quality or not. So these are completely different, let's say, goals that we are pursuing, and hence also the techniques that have been used and the results and also the methods of evaluation might differ. This was not really always the case, that engineers and speech technologists have been working separately on their separate goals. And one of the linguistic centers where definitely engineers were working together and also modeling directly, trying to implement computationally. They were trying to implement computationally quite directly in their speech synthesis systems. They try to implement their models of speech in computational systems such as speech synthesizers. Research centers like that, where, for example, my department at KTH in Stockholm, early in the 50s and in the 60s, when this man visible here on the right, Gunnar Fant, the founder of our phonetics lab there, speech, music, and hearing division right now, was basically starting his whole research journey. So he was both an acoustician, an acoustic phonetician, and a speech engineer and electric engineer. And he devised this first electronic speech synthesizer called OVA that you can see in the picture behind him, this incredibly huge machine. And this was a direct result of him modeling computationally his model of speech that he developed with some colleagues from Stockholm, that might be familiar to you, the source filter model of speech. So that was what you will see here is a modern, and here what OVA, that speech synthesizer, the very, very early speech synthesizer, sounded like. And you will immediately, hopefully, notice something about its naturalness. Let me check once more. So here the researcher using this interface is basically traveling with this arm around the vowel space continuum and playing the different values of the first and the second formant and synthesizing it using OVA. And it's working in the sense that you can hear that the vowel qualities are indeed differing as you move the arm up and down the vowel space continuum. But we can already say that however judged, whether from a linguistic point of view or from a kind of, let's say, customer's point of view, the quality, naturalness, realism of this particular speech synthesis system from the 60s is not particularly natural. However you define naturalness and however you measure naturalness, whether with MOS or not. But at that time, actually, speech synthesis was profusely used as a method in speech science. Actually, speech synthesis, this formant synthesis, speech synthesis methods that I just presented, which OVA is one of the representatives of, was very, very often used as a methodology in phonetic experimentation. For example, it was seminal in a very important categorical speech perception experiments. So people used in the 70s and the 60s synthetic stimuli using such systems that were simulating sound continua, in which categorical speech perception was demonstrated. So here in this picture, you can see on the x-axis the different manipulations from the category of a speech sound, speech syllable da to the syllable ta. And of course, the listeners in this identification discrimination task were listening to these 9 stimuli, which were manipulated using speech synthesis directly. So the voice onset time was increased or decreased in steps of 10 milliseconds from 0 to 80. And people were supposed to listen to these 10 stimuli and say whether they hear da or ta. And basically, that's how we could tell whether there is whether listeners hear a phonetic boundary. At which point will listeners hear the phonetic boundary between ta and ta? So the answer here would be they listen to 2 stimuli like that were manipulated and say whether they sound the same or whether they sound different. And the result of such perceptual experiment testing for categorical speech perception usually takes the form of such an S-curve, where usually the categorical perceptual boundary between da and ta happens somewhere around the time around the manipulated VOT, when the VOT is longer by 30 milliseconds, 40 milliseconds, and from 50 milliseconds, the listeners usually hear the syllable ta and no longer hear the syllable da. And in the middle, this dotted line basically shows the moment at which the listeners usually kind of guess whether this is a da or a ta. So there is a 50% difference, a 50% chance for guessing one or the other. So, however, what is worrying about those results, those early results, is that people have shown, particularly in this very, very thorough study by Winters and Pisoni, perception and comprehension of synthetic speech, that the results from categorical speech perception experiments might be potentially called into question, that they are not robust enough because the shape of this curve, or rather the steepness of this S-curve, which defines categorical perception, depends on the quality of the stimuli, of the synthetic stimuli. This is, of course, the result of the legacy systems, which is the formant synthesis, for example, having impoverished stimuli in terms of perceptual cues in general. So they basically do not model natural speech very well, as you have heard. And so these important redundancies that signal to the listeners, for example, some of the features that are important for categorical perception, these important redundancies in the signal are not preserved. So other people like Van Hessen and Schouten have actually, in 1999, have actually shown this quite directly by painstakingly constructing synthetic stimuli with this type of a VOT manipulation and comparing systems that preserve these redundancies a little bit better and formant synthesis. And they have shown that stimulus naturalness is certainly a factor that is contributing to categoricalness of perception. And so they showed that synthetic speech that is used in phonetic experimentation and such categorical perception experiments, if you have more fine detailed, if you have more natural synthesis stimuli, then this categorical perception curve will be a little bit sharper, in the sense that people will more readily and more robustly recognize the categories. Of course, we know that since then, also these authors, such as Hessen and van Schouten, have actually called the whole idea of categorical perception into question. So they suggested that results might stem from, first of all, the bias that is inherent in the discrimination task, that this discrimination task is actually highly task-dependent, and that other problems actually arise with categorical perception, that there is a bias regarding mapping to discrete rather than continuous categories in this task. But nonetheless, all evidence suggests anyways that we should aim for stimuli, that is synthetic stimuli, in these experiments, and by extension in all phonetic experimentation that is using speech synthesis, for stimuli that are as natural as possible if we want to learn anything about the perception of speech. So in 2009, we actually had a look at whether these days, when we have these data-driven neuronal network systems that are so much better in terms of realism and naturalness, at least when you listen to them impressionistically, or if you have a look at MOS scores, these very, very simple ways of evaluating realism, we thought, okay, let's perhaps have a look a little bit more deeper from a linguistic point of view, from a phonetician's point of view, whether these new systems are able to preserve these redundant features that are so very important for our experimentation right now, compared to the ones in the 60s. So we did for our ICPHS 2019 conference in Melbourne, we did this study in which we compared the systems that you see in the table. First of all, we took OVA, that is this formant synthesizer that was used also in the classic categorical perception experiments, or a similar synthesizer. We used OVA as a kind of a baseline, the bad baseline, a bad reference, something that is kind of, you cannot really go much worse than that. And then we compared a couple of other modern, at the time, systems. Remember, this was 2019. Today we have 2000. Well, it's already 5 years later. The systems that exist today are already much better, but the ones that we had a look at were already quite good. And of course, we compared the systems to a natural recording of the exact same utterance, because we had access to such data. We did a more sophisticated listener rating of quality called MUSHRA. If you are interested, I can give you the reference to that particular system, but it is basically a little bit more robust and a little bit more detailed in judging the quality of the stimuli than this very simplistic MOS score. And we also additionally judged listener behavior. That is, we presented people with stimuli from these different systems, speaking to words, for example, a list of pairs of words such as cat and bat, and the listeners were supposed to react as quickly as possible and say which word they heard, whether they heard cat or a bat. And we compared all of these systems to the natural speech and to OVA in that way. And what we have found was that what is probably really, really important is that this behavioral rating is really important in the sense that reaction times to vocoders, that is the speech generation, modern speech generation techniques, and Merlin TTS, which is a text-to-speech system that is also a modern system, did not reach statistical significance in comparison to natural speech, which means that people were processing the natural speech and the modern system output in 2019 as fast as natural speech. So there was no difference in how fast they process these signals, the natural signal and the modern systems, in this lexical decision task. This means that already at the time, modern text in, speech out, that is TTS, or speech in, speech out vocoder systems are being processed similarly to natural speech by human listeners. And you can imagine that 5 years later, this is even better performance. Right, so this is where we see that there was no statistical significance between these systems and the natural reference. Right, so this was a short survey of how evaluation of naturalness and what naturalness actually means has been happening over the years, and my kind of conclusion from the survey and part of a roadmap for speech synthesis. In order for speech synthesis efforts and to be useful for phonetics, my first, let's say, proposal for the future is to try and properly evaluate modern synthesis for the speech sciences. That is, try and evaluate speech synthesis, realism, naturalness, quality, however you want to call it, the performance of modern speech synthesis systems in a way that is meaningful for the speech sciences. How do we do that? First of all, we have to evaluate modern systems using behavioral and neurophysiological methods. For example, in a way that we did in this 2019 study, we have to go away from MOS, which is too simple, and have a look at things that are perhaps behaviorally meaningful, linguistically meaningful, and neurophysiological methods such as EEG and let's say monitoring the neuronal activity while listening to synthetic speech, or kind of reading while listening to a text-to-speech generated text would be really interesting and hasn't been really done much. What we also need to do in order to properly evaluate modern speech synthesis for the speech sciences is to evaluate the modern systems within phonetic prosodic practice. And we have synthesis challenges, so ISCA and Interspeech every year, not this year, but every year, exceptionally this year, there is no Blizzard challenge, which is this challenge for speech synthesis teams that kind of submit their best systems and compare their performance, and the best one wins. I think such synthesis challenges have been seminal and really important for the development and progress of in speech synthesis, but we also need, from a phonetician's point of view, to devise and add perhaps an evaluation paradigm to annual synthesis challenges that increases the scientific value of the tested systems. Okay, now I talked about a little bit how the different goals that the speech engineers and the speech phoneticians have, commercializing a system, presenting it to a user of a voice assistant, and speech scientists wanting to evaluate really finely grained features and kind of disentangle how people perceive the different features. Let's say if you have a prosodic task, you want to disentangle how people perceive pitch as opposed to some kind of acoustic representation of prominence. So really, we are really operating on different goals and on different levels, and hence we want different things from the speech synthesis that we use in our daily practice. Of course, as you may imagine, over the years, starting with OVE, this format synthesis system in the 50s, the industry needs, the needs of the customer, of the user, have kind of taken over, and they have informed and motivated the work of speech engineers and their speech synthesis systems. So the realism has been really getting a boost over the years at the expense of control of the speech synthesis system, of the speech synthesis signal, right? So right now we are at a point where we have highly realistic speech synthesis, but it is not very controllable. So there are no knobs which we can use and kind of turn in order to, let's say, bump up the fundamental frequency in a modern system, so that a voice, for example, goes up and down on every syllable, the way we could, for example, with OVE and the format synthesis systems. So the way for us right now, for people that care about introducing those modern, very realistic methods into phonetics, is to devise a future method which is both realistic and controllable. So what we need is an accurate control on a fine scale. And if you are interested in what this actually means, is you can also check that paper from 2019 where we list all sorts of different controllability features that such a speech synthesis system would have to have in order to be useful in phonetics. But what does it actually mean to control prosody if we refer to speech synthesis? Well, it seems that that people, again, from the speech engineering side and the speech and the phonetician side, understand controlling prosody in a slightly different way. So there are these developments on expressive speech synthesis, where controlling prosody means more controlling the collection of expressive factors of speech, such as intonation, stress, and rhythm. So the control of prosody here in these kind of part of speech engineering efforts operates on a rather high level. There are also other efforts which kind of take into account perhaps some things that are equally interesting to us phoneticians. That is, they are trying to model variables that are widely agreed to have a contribution to prosody on a very low acoustic level, things like F0, the length of the speech sounds, loudness, and the timbre and voice quality, measured using acoustic variables. And here we have two articles that kind of exemplify pretty well the high-level aspects and the low-level aspects that inform quite a lot of engineering work these days. Right. So we have this split a little bit here, but there is not much research in speech engineering that actually has a look at the relationship between these high-level aspects and the low-level aspects that we as prosodists know that definitely exists between speech style and how speech energy is distributed. And so there is not much work on trying to relate these high-dimensional forms to the explicit control of each disentangled feature. So there are some examples of highly influential work on that high-level aspects of expressibility. So, for example, these text-to-speech systems that are based on one of the kind of standards in text-to-speech, Google's Tacotron, they are able to learn via style embeddings, that is a lower level of representations of some prosodic features. They are able to learn in a non-supervised manner some styles that speech styles that exist in the data that they are learning on. And then by an encoder. And so in that unsupervised method, by learning the sort of pseudo labels of prosodic styles, these systems are able to control certain prosodic styles. But these prosodic styles that are learned from the data, they have to be interpreted by, let's say, a linguist or an engineer that is listening to those styles that the system is learning post hoc, in the sense we know that there are different styles and they are being learned from the data, but we kind of have to live with what the system actually has learned. So there are some researchers, such as, for example, Juraj Šimko's lab in Helsinki, that is trying to learn a little bit more about the relationship between the high-level aspects and the low-level aspects. But what is also common for most of these engineering efforts is that they are able to capture either the high-level aspects or the low-level aspects. That's one thing. The relationship is not very well researched. And also that the feature control is mastered more on the broad level, that is more on the utterance level. So we have quite a few systems that are able, for example, to hike up this pitch contour that you see in the middle. They are able to hike up increase the fundamental frequency over an utterance by, let's say, 300 hertz, or, for example, in such a way so that we can change between a male sounding voice and a female sounding voice, and so on, across the whole utterance, right? So this is kind of a broad feature control of prosody, of pitch, on an utterance level. This is these days using the modern speech systems that also have this very, very naturalistic quality that doesn't differ from natural speech, at least on behavioral measures, as I said, as we shown in our study. This is these days very much possible, and you can have many examples of such systems. But what about fine feature control, where we, as prosodists and as phoneticians in your daily practice, on your daily phonetician's workbench, what you would like to have, you would like to have a very naturalistically, realistically sounding system, but one in which you can also put an exact value of F0, or let's say a formant, the first formant or the second formant, on a chosen level, that is on a phoneme level, on a syllable level, on an utterance level, so that, for example, we can control prosody on a specific syllable or on a specific word. This is, I guess, what a prosodist or a phonetician would say fine feature control means. This is much harder to find these days. And so, for example, these are a couple of examples of current systems that have the realistic quality and perhaps could, after some tweaking, after some hacking of the system, also have fine feature control. So when you look into this architecture by Ren et others, fast speech and fast pitch from 2022, if you fiddle with it, at least in theory, you could modify the system in order to have fine feature control on a phoneme, syllable, word, and so on level. So that's possible in order to control the acoustic features. Other systems are by hierarchically conditioned, hierarchical systems that condition on utterance-wise pitch range, duration, energy, and spectral tilt. So they are able to, these examples of engineering work are able to control really quite a lot of low-level acoustic features. And they can control each prosodic dimension, generate styles, and control a word-wise emphasis. So these hierarchical models, like the one exemplified here, also hold quite a lot of promise. And coming to one of the last slides in this presentation, coming to my own work with Pablo Zarazaga and Lauri Juvela, we have set out to basically with the explicit intention, we have set out to work on our controllable and realistic speech synthesis system with an explicit intention to provide a method for phoneticians in the future to work with that will challenge, so to speak, the legacy systems that phoneticians have been using right now when they are manipulating pitch, when they are manipulating formant frequencies and so on. So the legacy systems that phoneticians use these days are Psola and Embrola, as far as I know, as we have kind of surveyed a couple of colleagues. This is what is being used, using, of course, the interface that is available and the implementation available in Praat. And so Praat is kind of our the reference and the system that we want to beat in terms of in our work, in terms of the controllability and how well the features can be manipulated. In terms of realism, we have already shown, and these systems have been improving a lot. That this benchmark of naturalness and preserving the natural redundancies in the signal has already been beaten by the modern systems, but the manipulability of the finely grained features is the problem. So we have devised this speech in, speech out system. So you put in a recording, and then you can manipulate the recording and resynthesize the manipulated features, the manipulated and kind of generate a manipulated signal. So we propose this neural formant synthesis system, which is a speech in, speech out system, which allows for explicit control of formants with high realism. And we do that by introducing a feature mapping model, which is learned, and we evaluate the system against Praat. So we are working right now, and this is forthcoming. We have so far in the system of neural formant synthesis that we published in 2023, we used a ready-made out-of-the-box signal generator that is a neural vocoder. But kind of particularly the quality of the signal is kind of limited by progress in vocoding, and also does not allow us for a kind of a fully blown controllability features. So we decided this year to construct our own vocoder, which is specified towards this goal of formant control, and also following the source filter model structure, which you may remember I mentioned. That was also the inspiration for modeling for Gunnar Fant. So we're kind of coming back full circle and trying to leverage both the modern architectures and construct their source filter model structure using neural networks. Right. So the results, we compared our system to particularly the manipulation feature to how Praat is manipulating low-level features. That is F0. You see in the panel of the results on the top left. So we have a look at how Praat manipulates fundamental frequency and the first formant and the second formant. Let's concentrate on these results now, finally here. And so in blue, on the y-axis, you have the mean score error of z-scored speech features, either F0, F1, or F2. That is our measure, and the higher the error, then the worse the performance of the system. So you can see in terms of fundamental frequency, we are doing as well as Praat, because the red boxes are basically equally. There is no significant difference between the red boxes and the blue boxes, which represent blue boxes represent the reference in Praat. And we manipulate the F0 feature and the formant frequencies by basically scaling the formants by a factor of 0.07 or 0.8. So we lower the pitch or we hike up the pitch, and see how well the manipulation is then realized depending on what we dictate to the system. So as a final thing, I can show you the samples, and I'll stop sharing now, or maybe I can leave the samples if we have some time. Then I can present the performance of the speech synthesizer in the question time. Thank you.
Thank you, Zofia. I think it's better to you to us to present the audio files.
I'm sorry, but there's echo. No, I cannot hear you, Plinio.
And now? Well, já tá.
Shall I play the audio files now while you maybe I'll just play them, okay?
Yes.
Okay, now you can hear me. So this is this is a GitHub page with our demo of the neural formants synthesizer that is able to control formants and F0 on a fine scale. At least we are trying to go towards it. And the first evaluation task that we did here was to make sure that when we use the that our system is not really interfering with the quality of state-of-the-art modern synthesis quality, right? So the first evaluation task that we did here was to ask listeners in a subjective evaluation task to listen to a natural reference, to listen to a standard signal generator such as the Hi-Fi GAN vocoder. So here you have and say basically and rate on using the Mashra evaluation system that is more robust and more finely grained than MOS, how they rate the naturalness of the signal. So the reference signal is of course taken from a speech recording, and I'm going to play it now.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
Did you hear it well, or I'll repeat the reference once more, the natural reference?
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
Yes, we're listening perfectly.
Okay, and now I wanted to play an example of a state-of-the-art vocoder without our neuronal formant synthesizer control attached, which is just a resynthesis using that vocoder, in this case WaveNet, resynthesizing this reference signal.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
And another example will be the same vocoder, which is WaveNet, with our system attached. And the task of the listeners was to say, how natural do you judge the signal? And we found that there are no significant differences, in the sense that the listeners do not judge the vocoder with our system attached as less natural than just the vocoder. So that was just, let's say, a reality check in terms of naturalness rating.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
Quality itself, as you may hear, is not that great, but it also has to do a lot with the data, which was data taken from a data set that was recorded podcasts, not really super lab quality, but it was important to us that it was a multi-speaker corpus. So let me give you another series of comparisons. This is the natural reference.
The difference in the rainbow depends considerably upon the size of the drops, and the width of the coloured band increases as the size of the drops increases.
This is the state-of-the-art vocoder resynthesis.
The difference in the rainbow depends considerably upon the size of the drops, and the width of the coloured band increases as the size of the drops increases.
And lastly, this is our system with format control and the state-of-the-art vocoder. And here the point is that the quality should not be worse than what you just heard.
The difference in the rainbow depends considerably upon the size of the drops, and the width of the coloured band increases as the size of the drops increases.
Okay, and now for the manipulation evaluation, I can show you, oh, sorry, what happened? I can take some questions while I recover my manipulation samples from the web.
Okay, thank you. Thank you so much, Zofia, for your presentation. We have about 10 minutes for questions from the public, from the YouTube platform. You have already a question for may I ask to you, Zofia? From Julio. He has the following question. Given the complexity and opacity of deep neural network layers, how do speech synthesis models map extracted acoustic features to linguistic units, and what methods are available to verify the accuracy of these mappings?
How do speech synthesis models map extracted acoustic features to linguistic units? I mean, they do not do that these days. That's the thing actually that is making it really hard to construct controllable speech synthesis methods, because we have been in the pursuit of naturalness and realism. We have been removing signal processing modules, linguistic features like the linguistic units you're talking about that used to be informing the speech synthesis systems. Still 6-7 years ago, when we have the statistical parametric models that worked a little bit more like you talking about here, Julio, that is that we had extracted acoustic features and we had the text, and we extracted the linguistic features and representations, and we're mapping the linguistic features to the acoustic features and so on. That was working pretty well, but soon people found out that so-called end-to-end systems, which get rid of all sorts of information that might come from a linguist, and you know, all sorts of signal processing modules, then they found out that if everything is learned by a highly sophisticated, from data, by a highly sophisticated neuronal architecture, and they were kind of progressing, the different architectures were progressing rapidly, that these end-to-end systems, the so-called end-to-end systems that basically map the almost like just the Mel's spectrogram to some representation of the text, that these have very high realism. And so this is really I'm not sure. I think what methods are available to verify the accuracy of these mappings. I think in order to answer this part of your question, I think a lot of promise lies in what I guess I exemplified in the work by my Finnish colleagues in Helsinki, in trying to relate and kind of to walk down when you have a look at what these modern systems are learning in terms of representation in the embedding space, and try to see what consequences it actually has, and try to discover and interpret what are the consequences of these representations in the low acoustic space. But this is really, really difficult and requires quite a lot of, let's say, mathematical skill more than any other, in order to be able to kind of uncover what the model actually is learning when the model is learning some sort of an expressive prosodic style in the output.
Thank you. Gerard Bailly has a comment for you. I think you can read in the... That's what I suggest. Probe models to study the mappings. Yes. That is, superpositional models are good models since feed-forward transformers do this job. Mm-hmm. He added causal regressions, latent space analysis, etc.
Yes. Okay. So what I meant exactly. So what I meant is the latent space analysis, right? So you can check the work that was also that is going on. Regarding the latent space analysis, I think that is what is going on right now to uncover that relationship, which is a really important part, because, as I said, quite a lot of engineering work has been put into modeling those high level aspects like expressivity, style, some things that are kind of, you know, a composite of prosodic representations, that's qualitative. And there's quite a lot of work that goes into controlling low-level acoustic features like fundamental frequency. Formant frequency is harder. And but the relationship between the low acoustic level and the expressivity level or the style level, and how to basically model this is a very promising and hard question that I would encourage you to follow.
Okay, thank you. Thank you so much, Zofia. It's 3:05. I think you should end your lecture. I would like to thank you again on behalf of the Speech Prosody SIG, Easter SIG group. Thank you so much. And if you please, Gustavo, share the link in YouTube. She's given to everybody.
Yes, you can have a look at the manipulation samples there, yes, because I managed to present that.
Okay. And thank you so much. And Gerard Bailly, I will invite you to a talk. Thank you so much for offering yourself to talk to us. Thank you so much again, Zofia, and see you. I hope I can see you in one of the next conferences in Europe.
Yes, definitely.
Thank you so much.
Thanks so much again for the invitation.
My pleasure. Our pleasure.
Good.